All right, let's take a journey to the very edge of reality, shall we? We're diving deep to understand one of the universe's most profound, and let's be honest, most terrifying mysteries, the black hole. This is a story that doesn't start with supercomputers or giant telescopes. Nope, it starts with a wild thought experiment way back in the 18th century, and it ends with us, today, literally staring into the abyss, thanks to the first ever photograph of one.
Everything, and I mean everything, we're about to talk about starts with this one simple question. It sounds kind of ridiculous, right? Light is the fastest thing there is. Nothing beats it. But what if gravity, the most relentless force in the cosmos, could actually win that race? This question, this little what if, is the seed that grew into our entire understanding of black holes.
So you probably think of black holes as a modern concept, something that popped out of Einstein's mind-bending theories. But the idea, the first little glimmer of it, was actually planted way, way before that, in an age when we were just starting to figure out our place in the cosmos.
Let's go back to 1783. There's a scientist, John Mitchell, and he's just thinking about Newton's laws of gravity. He doesn't have a fancy lab or a computer, he just has his own mind. And with a brilliant thought experiment, he stumbled onto a concept that is the key to all of this: escape velocity.
So what in the world is escape velocity? Well, think of it like this. Gravity is like a leash. If you fire a cannonball from Earth, you have to shoot it really, really fast to break that leash. If you're too slow, it just falls right back down. But if you hit that perfect magic speed, it's gone. It just keeps going, sailing off into space. That critical speed, that's escape velocity.
And here's the key thing to get. The more massive something is, the stronger its leash. Earth's escape velocity is a pretty zippy 11.2 kilometers a second. But Jupiter is a giant, way more massive. So to escape it, you need to be going a whole lot faster. And our sun? To break free from the sun, you'd have to hit a blistering 615 kilometers per second. You see the pattern here, right? The bigger you are, the harder it is to get away.
And this is where John Mitchell had his stroke of genius. He just took that pattern and pushed it to its most extreme logical conclusion. He asked, what if a star was so incredibly massive and dense that its escape velocity was faster than the speed of light itself? Think about that. Light travels at 300,000 kilometers per second. If the leash is stronger than that, then not even light can escape. The star would be totally invisible to us. He called it a dark star, an absolutely incredible idea centuries ahead of its time.
Okay, so Mitchell's idea was just that, an idea. But how does the universe actually build one of these monsters? Well, the answer is found in the fiery, dramatic death of the biggest stars in the cosmos. For billions of years, a giant star is in this perfect state of balance. It's a cosmic tug of war. Deep in its core, nuclear fusion is constantly creating a massive outward push of energy. But at the same time, the star's own incredible gravity is trying to crush it inward. Outward push, inward pull. As long as those two forces are equal, the star is stable and happy.
But that cosmic balancing act can't go on forever. The star burns through its fuel, fusing elements until it eventually makes iron in its core. Now, iron is a dead end. It's like cosmic ash. You can't fuse it to get more energy. So, just like that, the outward push from fusion, it just stops. And with nothing holding it back, gravity wins. In an instant, the core collapses, and the outer layers of the star explode in one of the most violent events in the universe, a supernova.
What's left behind after that explosion is what really matters. For a star like our Sun, it would leave behind a small, dense core called a white dwarf. A bigger star leaves behind an even denser neutron star. But for the true giants of the universe, stars more than 20 times the mass of our own Sun, their gravity is so powerful that once that collapse starts, there is nothing in the universe that can stop it. Absolutely nothing.
Now, to really feel how insane this collapse is, let's just think about our Sun for a second. It's huge, right? About 1.4 million kilometers across. You could fit more than 1 million Earths inside of it. Just try to get that massive scale in your head.
Okay, you got it? Now imagine taking all of that stuff, the entire 1.4 million kilometer Sun, and crushing it, and crushing it, and crushing it, until it became a black hole. Its diameter would be just 6 kilometers. The entire mass of our Sun squeezed into an area smaller than a medium-sized city. That is the mind-boggling density we're talking about here.
For more than a century, this dark star idea was just a weird little curiosity. And then, in 1915, this guy named Albert Einstein came along and completely rewrote the rules on gravity with his general theory of relativity. And all of a sudden, these dark stars didn't seem so weird anymore. They
They seem terrifyingly real.
See, for hundreds of years, we all thought about gravity the way Newton did, some kind of mysterious, invisible force that just pulls things together. Newton could tell you exactly how it worked, but he had no idea why. Einstein's answer was just revolutionary. He said gravity isn't a force pulling you, it's the shape of the universe itself. Einstein imagined that space and time are woven together into this four-dimensional fabric he called space-time. The easiest way to picture it is like a giant, stretched-out trampoline. If you put a bowling ball, like our sun, in the middle, it creates a big dip. Now, a smaller ball, like Earth, isn't being pulled by the bowling ball. It's just rolling along the curve in the trampoline fabric. That is what gravity is.
So, what does a black hole do to that space-time trampoline? Well, it doesn't just create a dip, it punches a hole straight through it, a bottomless pit. The event horizon, that's the edge of the pit. It's not a physical thing you can touch, it's the point of no return. Once you cross it, the fabric of space-time itself is falling into the center faster than light. Every possible path you could take leads to the middle. There is literally no way out.
For decades, this was all just incredible, mind-bending theory. Even Einstein thought the whole idea was probably too weird to actually exist in the real universe. But astronomers are a stubborn bunch, and they started to hunt for evidence of these invisible monsters lurking in the dark.
At first, the clues were just whispers. In the 60s, we found these things called quasars, these unbelievably bright jets of energy that seemed to hint at something huge and powerful at the centers of galaxies. Then we started seeing stars orbiting, well, nothing, wobbling around an invisible partner. But in 2015, those whispers became a shout. We directly detected the ripples in spacetime, gravitational waves, from two black holes that collided 1 billion years ago. The proof was right there. And then finally, we actually saw one.
So how on earth do you take a picture of something that, by its very definition, eats light? Well, you can't. You can't photograph the black hole itself, but you can photograph its silhouette, its shadow, cast against all the superheated gas and dust swirling around it right before it disappears forever. And the solution was honestly one of the most amazing things humans have ever done: the Event Horizon Telescope. It's not one telescope, it's a whole network of them, all across the planet, all working together and synchronized to act like a single virtual telescope the size of the entire Earth. This planet-sized eye stared at a galaxy 55 million light-years away, collecting unbelievable amounts of data, which, when finally put together, gave us that iconic, world-changing picture.
So we've seen the shadow, but what's in the middle? What's at the heart of the black hole? Well, our theories predict something called a singularity, a single point where the entire mass of that dead star has been crushed down to zero volume and infinite density. It's a place where all the laws of physics as we know them just break.
And that brings us to one last, truly wild question. We think our own universe started from a singularity, right? The Big Bang. And we know that giant stars create singularities when they die. So is it possible that our whole vast universe is just what blossomed out of a black hole that formed in some other older universe? We don't know the answer, but it's a pretty powerful reminder that sometimes the biggest mysteries out there are the ones that hide the deepest truths about everything.